Hello, everybody. Welcome to Mankind in Training. Sorry I've been away for so long. I've been really busy with school. I keep getting some doozies, some classes. Currently in a software engineering one, and the one before that was algorithms and things, and they took a little bit more of my time. I didn't have as much free time. I haven't been able to make the videos. So sorry, everybody. Um, I want to begin this video so at the end of the last video, we had some questions that people had paid to get answered, and I left out Isaac Newton, and I feel bad because I was trying to be very specific to quantum mechanics, and Isaac Newton is more like the father of like all physics, I guess, um, as he invented integral and differential calculus. Because he was trying to solve the problem of how far away these other bodies in the universe are and how they move and how to describe that movement and the motion of the heavens. And Isaac Newton deserves his due. So he's a giant as well, and I should have mentioned him a little more, and maybe should have even put him over top of John von Neumann. But so that's one thing I wanted to clear up. Isaac Newton is absolutely a giant as well. So today's quantum field theory. I'm gonna teach you guys a little bit quantum field theory, combination of quantum mechanics and the combination of general relativity as given to us by Einstein, description of gravity, trying to combine these things. And so I'm gonna give you guys a little bit of what's going on here. Um, where did I go? All right, like over here. Okay. Put this back up here and this back up here. So first thing I'm going to do is I'm going to give you a representation of some quantum mechanics, and we're going to do that by the following. So I and H bar, and then you get these, and we get partial derivative with respect. Just go ahead and get rid of that. Ah, will you just stay there, please? With respect to time. And then I'm going to give ket psi equals, so it's this, so h hat, and then the other ket psi. And this is Schrodinger as a representation of quantum mechanics being combined here with now general relativity. And I'm going to just write out a simple gamma equals, let's see, 1 over root 1 minus v squared over c. So come on, stay there. V squared over c squared. Ah, not like that. Like, whoa, what's going on here? No, I need you to be, there we go, right there, slash c squared. So, this is special relativity, sorry, and general relativity. We're gonna get to that later. So, a particle per se does not have particle not have a definitive position. Instead, has a probability distribution in the form of a wave. And wave mechanics is all these different waves, these fields are all interacting, and that is the universe in which that you're seeing and currently stuck in. And in it is electrons and quarks and antiparticles also. And so the crazy thing is, I think the number is something ridiculous, like 4% of the universe is matter. Like actual fermions and things that interact with photons that you see on a daily basis, stars and planets and the things that make up us is only 4% of the universe. So the other 96% is dark energy and dark matter. And we have no idea what these things are, but we know that they exist because of I've explained this in other videos because of the way that the galaxies are behaving and how they stay together and how they are moving apart faster than the speed of light. And we have evidence of both of the fact that there is dark matter keeping universes held together, and there is dark energy accelerating the propulsion of galaxies away from each other relative in position. So we know that these things exist. So what the things that I'm about to get into are everything that make up the universe, but only like the 4% part, and then the rest we are still trying to figure out. And so inside of these fields, there are a bunch of things that are interacting, and they have various different spins. Like zero spin is the Higgs field, and then we have 1/2 spin, that is fermions. Fermions. And that is quarks, electrons, neutrinos, and muons. Neutrinos and muons. Yeah, that's what I'm missing. Muons. So that is like stuff, physical stuff has half spin, integer spin stuff. Now, so half spin things that I just described are also spinners, are spinors. Ah. Now we have integer spin items like photons and bosons, and those are vectors. Nosons, botons, vectros. And then we have 3/2 spin items, and these are two spinners. And I believe those are oh, so photons, bosons, and gluons, I think were the vector, or no, so yeah, I think that's how that works. Two spinners are these gluons, and then we have two integer spin two vectors. So like when a photon and a boson interact, I get a two vector to describe something like that. Electrons have a mass of 9.109 times 10 to the negative 31 kilograms, and they have a charge of Q equals negative 1.602 times 10 to the negative 19th times the constant. Fields must conserve energy, have internal and external symmetries. Particles are distributions or are disturbances in the field. Also, virtual particles are being sorted through the fields all the time. The different fields all interact, creating the collective wave function of the universe, combining the probability, density, and amplitudes of the various fields, and the average objective reality that surrounds us all adds up to what you see on a daily basis. So I have to set this down for a moment. I will be right back in just a second. Sorry, everyone. I had to check that for a moment. So now we're on to. I was on page 2 of our quantum field theory notes that I took for you guys. So, the standard model of particle physics is what we're going to do now. This is the following. So we got some quarks, we got some different kinds of quarks. There is the U up. There's the C charm. There is the T top. There is the D down. The S strange. And the B bottom. And then we have some leptons. And that is like electrons. E, sorry. E electrons. Missing an R. No. Let's go here. Let's go. No, wrong position. Here we are. Electrons. E electrons. And then we have the mu muons. And then we have the T tau. We have the tau tau. Tau tau. And then we have the V subsystems. I hate how it goes to the top every time you do that. V, it's like one of the only things I don't like about well, that, and that is your electron neutrino. And then I think this is what I'm trying to do. I think that is what it is. Yep. This is when we got it. Muon neutrino. Neutrino. And then we have the tau neutrino. Yeah. That's tau neutrino. That's the end of our neutrinos. Now we have some gauge bosons. Bosons. Huh. Okay. Gauge bosons. And that's G gluon. Oh, whoops. I did this before. Stay consistent, Josh. And then we have G gluons, which are super important, like the neutral particles that the uh, positively charged and negatively charged cloud positives and the neutrals attract into your uh why am I blanking out on this word? That's nuts right now. Nucleus. They make up the nucleus of the atom, and without gluons, we would not have any mass. There's all kinds of problems without gluons, and electrons and protons make up what we need to survive and be alive here. So now we have the gamma photon, and then we have the Z and W bosons, and then we have the 8 Higgs field, which is all by itself. It's a scalar boson. H for Higgies. All right. That is what's going on with that. Quarks, leptons, physical stuff. Looks like my screen's totally froze. Not sure how long that's been like that. Maybe I'll just get rid of that. Okay, so back to it. Now we have I'm gonna write down Einstein's general relativity for you so we get a little understanding of some things. Hate that. R mu nu all right. Minus 1/2 our G mu nu equals 8 pi G T mu nu. So that's Einstein's theory of how gravity interacts with things. So you got your uh your G mu nu of x and t, and that actually describes whoa. So space, time, and the gravitational field and its indices, mu and nu. And then we got things like the vector E, x and t, and the vector B of x and t is electromagnetism, electromagnetic fields in action. And then you're all like of x and t, and it's all like, whoa, space, time. And then we're gonna go electromagnetism. Gravitational field. Gravitation. Yep. And then, so let's go to paint real quick. This is where Isaac Newton's pretty awesome. So we got this is the sun here. Fiery, fiery sun. And then this is our little blue dot of an Earth. So how gravity is working here. You got a force. You got sigma of the vector F equaling m in the vector A. M in the vector A. And then you got a rule saying, so F will be proportional to m over r squared. So we are, so the force of gravity drops off proportionally to r squared. So the further you are away from something, the further the r distance squared, the less gravitational force will be exerted from either side. So everyone likes to think that the sun is just creating this big bowl and we're stuck in the bowl. But in all reality, the earth is also making a small bowl. And these two bowls are kind of like intersecting at a point. So if I could kind of describe that, the earth itself is making a little indentation like that. And then the sun is making a big indentation. But the two of them overlap at a point and then create kind of a well that holds the two wells together. But the farther you get away, this could be separated entirely. There is no more overlap anymore, and then the well of one does not interact with the well of the other. But it drops off proportionally with r squared. And then this is another thing you want to keep in mind. This is a rule that Einstein gave us, is that v is always going to be less than or equal to c. C being the constant, the speed of light. So v can't be greater than c. It can be only less than or equal to c. So now let's get into the Klein-Gordon. Let's do the Klein-Gordon theory, because that's kind of like important. So where's my thing? Phi of x and t describes phi of x and t describes a place for a wave to exist, or a field, and the fields to interact. Space times over here. And then you got some kind of thing that's got a mind of its own. It's high there and steep. corners. This field is distributed over all of space. And as you can see, these high points are probably positions of the least energy of a particle of some kind. And all of them are interacting with each other. And then in the sense of quantum mechanics, none of them are like actually have a position. At There's only a probability that they're at a variety of positions, and then all of those things are combined into a superposition of states, and that's how it is until it interacts with something and is measured, or uh, just the fact that it's becoming entangled with its surroundings itself will disrupt it. The surroundings absorb, and it becomes part of the wave function that we measure, you know. So in this arena of phi and x and t is where these things happen. So I just want to do this real quick. As the sun's barreling through the galaxy, all of the planets are along for a ride, so it's not a simple circle like that. It's going to end up being a corkscrew through space. But so let me finish that line. And then the sun will have a much subtler. But anyway, so back over to Wolfram so I can type some things out. I'm going to get to Lagrangian mechanics because that's a good way to represent what's going on particle over time. What happens to a particle over time? And that's going to be my Lagrangian L, and it equals uh, ah, that's dumb. Not what I did at all. There we go. Equals 1/2 m. Of course they don't. Um, just to be clear, I'm gonna try to do everything as clear as possible. And these have they look. There we go. They look like they're supposed to be what they're supposed to be. The derivative x with respect to time squared. Oh, uh, this stuff's really weird. It is kind of hard to write some of these things out. Minus u x. So we have kinetic energy here and potential energy here, making up the Lagrangian. And there's a Lagrangian density that's the difference between the two. And then we have an action, which is the integral of a derivative. So it's how did I do that there? How did I do that there? I don't remember. And then we have I should have just did that one because it is exactly that. So but the problem is it's gonna take forever. Sorry guys. The Really right now? And then Do it again. TF. All right. I think it's supposed to be backwards from that, like the L is supposed to be after it, but it wouldn't let me put it in like that. But this is the action of the integral of the derivative, the difference between the potential and the kinetic energy as measured. See if I can draw you guys up something else again in paint maybe to make up what's going on here. S equaling the number, and then you got so like F prime of X is not, and then you got X plus epsilon, and then you got DF equals F prime of X epsilon equals 0. Lagrangian mechanics, Klein Gordon. So then we're going to take the D. No. We're going to take DL equals M dx by dt dot d epsilon dt. The difference change from in space, and then epsilon is the little changes over time, minus du dx times dot epsilon. So du and dx, and then we're going to give you an epsilon or dot epsilon. So then you get so dx over dt transforms to dx over dt plus d epsilon over dt. Plus d epsilon over dt. And the difference. And then you got Lagrangian density, your DL. Ah, why did it do that? Yeah, they make everything so difficult sometimes. No. There. Why is it saying that? Mm, mm, minus Uh, plus the derivative with respect to time. Uh, M epsilon. And then there's the action, S. No, 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 no. So ds, Buenos Dias equals uh, this, pretty much. Pretty much this right here. Of and so yeah, all of that there. So this is field theory, x and t, x of t, the function x of t turns into phi of x and t, the function of space and time, and then returns a numerical value. Phi is always going to return a number. Has the same action, kinetic and potential. The difference is the Lagrangian density. Um, the Lagrangian phi, comma, the partial derivative phi with respect to x, the partial derivative phi with respect to time. K, curly k, minus curly u. These are energy densities. They use the gradient energy. And then the k is like the wave numbers. So curly k is 1 over 2c squared, partial derivative phi with respect to time squared, energy density. And then curly u of x is 1/2 partial derivative phi with respect to x squared plus 1/2 kappa squared phi squared for the gradient energy. And that's what we're doing to get everything bundled together in quantum field theory. Every particle has a field, a resonant field, and it's in one of the energy states that that field could be in. It's in a superposition of all of them until it's interacted with the rest of, what's going on here. Mysteries, mysteries, mysteries. What is the other 96% of the universe? And I've been trying to work on some of these things, but it gets hard. It's difficult. Props to Isaac Newton, though, and props to Albert Einstein for helping us figure out how all these things interact. Remember the gravitational wells interacting, fields interacting. Go over this real quick again. I am the host, Joshua Parr. Thank you, everybody, for watching. I appreciate you guys coming to these. I appreciate the donations. I appreciate the suggestions. I love suggestions. We're doing some experimental things, and I would very much love suggestions. We have a small budget, and I would like to take suggestions from the public. If you think you have something you'd like to see done or a problem you'd like figured out, we can absolutely help on projects. Thank you, everybody, for watching. Quantum mechanics. mixed with special relativity, and I told you about the fact that particles don't have a definitive position, and they don't always have a definitive, well, they have properties, but those properties can be changed relatively easily. So, in the sense of its spin and charge, and the charge usually is a fundamental thing, but it's what happens with the charge, the spin, and its angular momentum all make a difference in the wave and how the wave will interact with other waves. 4% of the universe, the parts that I'm talking about, that's it. The rest is 96% of the universe is dark energy and dark matter, and we have no idea what's going on. But people like to think we know everything. The more I learn, the more and more I get into how complex even like single cell organisms are. And then you get to multi-celled organisms, and then you get to like human beings and our brains and the fact consciousness. I, it's it's epic. It is epic. Our brains are the most powerful computers and most efficient things that have ever been designed. And they have to have been designed. That's what I think for sure. There's a God, no doubt about it. Everything is so beautiful and perfect and works together in harmony and is complex. This is the perfect place where I can speak out loud and you guys can hear me. And now I can send it through wires over the internet and the whole world can hear me if we spread it enough. But there's a God out there, undoubtedly, who created all of these things. And the more I learn about it, the more I am 100% certain that this all could not have come together without a design, a specific design. The human mind, if you tried to create it right now, would take up like the size of several city blocks, and it would need an outrageous amount of energy to use, and it would need to be cooled with a whole river full of water. And there, our brains run on I forget the number, but our whole body runs on a very extraordinarily low amount of electrical charge that is sent through neuro pathways, and you have various different neuro carriers in your blood and in the rest of your body. Your nervous system works with chemicals and things, and it operates. It's the one of the most. It is the most efficient machine ever created, the human mind. We we are very, very, very far away from making other things that are as efficient and powerful as the human mind. Think zero. Higgs field is just like uh just a round object, and then you get the next over half spins have some property like that, and those are spinners. And then this is a vector. These are all the things that can interact in fields. The Higgs field is everything's in the Higgs field. So then you got these half integers, spinors, like fermions and things. And then you got vectors, the full spin in full integer spin, and then you got 3/2 spin, 3/2, and that is a two spinner. It's got directionality like that, and then it's got two possible uh probability density directives with the momentum like that, or they could be facing the other way, or there's there's a lot of ways that could go. And then there's two, which is just a straight two vector, and it doesn't have the orientation of like a spin like that one does. Just two vectors that they probably collided here, and now one's on this trajectory, and now one's on that trajectory. Thank you, everybody, for listening. I'm going to make another one. Um, I'm going to make another one later tonight. Sorry, I thought I thought I stopped sharing entirely, and I was like, oh man, I didn't mean to do that. I'm going to make another one later. Project about making it's going to be programming. I'm going to make a I already have started making it. It's a project for my software engineering class, and I'm going to take you through the entire thought process of designing a game, a very, very simple game. So I'm going to show you how truly complex all of this is, all the way from down to up. I started the very first thing I did in the design was what's it gonna look like? I wanted a text-based console RPG game where you have a player and you fight monsters and other characters and you can get gold and you can there's magic and you can level up and there's a save game and there's a lot to the design of everything actually, but in a game that doesn't even have graphics, it's just all text still it's still very complex and hard to write together. So I'm gonna take you guys through the process. I'm still not even done with the project. I'm still working on it. So you guys are gonna actually get to see me, doing it really, because I still haven't finished yet. So thank you everybody for watching Mankind in Training. I'm gonna try to teach you guys as much things as I can. I take suggestions. If you'd like to message me here on Facebook, or I have my contacts in the descriptions, you guys can get a hold of me and I will do whatever I can to explain whatever you guys want. Or you guys can ask questions for the Q&A episodes. There's going to be another one soon. I already have 7 questions. Waiting for at least 10. So just send me 3 more questions and we'll have another one of those. I'll see you there.